Hello everyone, I am Samruddhi Ambildok. Today I am here to take you through our project on stochastic optimization model of distribution companies by utilizing flexibility of electric vehicle aggregator with my batchmates Zaid Bagwan, Ali Mohammad Pathan and Shrutika Supte. Here I will be briefing you through the index which includes the aim and objective, basic idea about what is aggregator, the block diagram and methodology of the optimization model as well as the optimization model with its nomenclature. Lastly, we will look over to the project outcomes, conclusion and references.
Now, let us take a look into the aim and objective. The aim is stochastic optimization model for distribution companies by utilizing the flexibility of electric vehicle aggregator. The objective is basically this model is proposed to reduce the operational cost by fully utilizing the flexibility of electric vehicle aggregator. Here, stochastic optimization is applied to evaluate the costs that have been affected by uncertainties in renewable power outputs and EVA charging demands. By using EVA, we can mitigate the uncertainties of renewable energy sources and electric vehicles. Now, let us understand what is meant by an aggregator. Aggregator is nothing but basically a middleman between an electric vehicle owner and distribution company. It manages all the data that is related to electric vehicle and distribution companies. It is also influenced by many factors including human decisions. They involve considerable uncertainties. Lastly, it is more reasonable for system operators to dispatch EVAs and let EVA control a limited number of EV and adopt such schemes.
So here is the block diagram of our proposed model. So as you can see that the discoms are being tasked with meeting the real-time and day-ahead electricity demands of consumers. As you can see, the discom has been powered by the transmission companies, renewable energy sources and electric vehicle aggregator. Here, as we incorporate the renewable energy sources and electric vehicle, it alongside introduces certain unpredictable uncertainties. In order to manage these uncertainties, electric vehicle aggregators are being tasked to optimize the cost and mitigate the penalties for distribution companies. By employing the stochastic optimization techniques, we focus on minimizing the penalty cost and uncertainties by generating scenarios wherein the renewable energy sources is kept constant while varying the uncertainties associated with the electric vehicle adoption and vice versa. So, here we will see few basic terms associated with our proposed model which are being incorporated in our real time and day ahead values. So, here we'll be seeing the stochastic optimization model. Basically, stochastic optimization is a powerful technique that addresses uncertainties by incorporating probabilistic elements into the optimization process, wherein we are focusing on creating various scenarios which tries to optimize the uncertainties being incorporated by the renewable energy sources and the electric vehicles. More the number of scenarios being generated, higher will be the accuracy. So, here is the objective equation. The objective equation focuses on minimizing the total operational cost of the distribution companies, wherein we have added the day ahead and the real time values. In day ahead cost, we added up the cost of the energy being imported by the Transco and discharging energy from electric vehicle aggregator. Cost of the renewable energy is being proposed model has been neglected in both the day ahead and the real time values. In real time cost, we have found out the probability factor of numerous generated scenarios. Each scenario includes cost of penalty incurred on DISCO by transmission companies along with the cost of deviation of energy coming from the electric vehicle aggregator in order to shift the charging demands and mitigate the uncertainties. Now let us see the day ahead constraints. In day ahead constraints, we have power balance equation which is framed by studying the forecast in day-ahead stage where EVA acts as source or load depending upon the need and power imported by the transmission companies along with the power generated by the renewable sources that satisfy the load demand. Now let us see the real-time constraints. Here we have two equations. The first equation resembles the power balance equation and the second one is the auxiliary equation which is a combination of power of electric vehicle aggregator and uncertainty caused by incorporating electric vehicle aggregator. We also have a linkage equation for the day ahead and the real time parameters and variables, where whenever there is any deviation of energy generated in the renewable energy sources, then it will be overcome by the power of the electric vehicles. And if the uncertainty is beyond the capacity of the electric vehicle aggregator, then power imported by the transmission company has to be deviated by high penalty charges. Electric vehicle aggregator not only mitigates uncertainties of renewable energy sources but also mitigates the self uncertainties.
Here are the few graphical results this of various case studies. This is the case 1 which are the results for without EVA flexibility. The following graph illustrates that regardless of uncertainty, the planned value for EVA remains constant in real time. It indicates lack of flexibility in EVA model. The next is the case 2 which shows the results for zero EVA uncertainty using EVA flexibility. In order to reduce the uncertainty, we have used EVA flexibility in real time. We are considering the uncertainty arriving in EVA is 0. Next is the case 3, which are the results for charging EVA uncertainty using EVA flexibility. Here, positive charging uncertainty is defined when very less number of EVs are available so that the energy received is comparatively less. Next is the case study where results for discharging EVA uncertainty using EVA flexibility. Here, negative discharging uncertainty is defined where more number of EVs are available so the energy received is comparatively more. From the above results, we can see that the highest cost is incurred without EVA flexibility and least is incurred while zero EVA uncertainty using EVA flexibility. Next is the case where we are comparing the results of zeta constant varying renewable energy. Here, zeta is the uncertainty of EVA coming due to availability of connected EV to the aggregator. The following graph shows the result where zeta is kept constant and RES keeps on varying. These are the scenarios that have been generated and the following distribution companies operating cost. Next is the case where RES is kept constant and zeta is kept on varying. Here the following graph shows the result where RES is kept constant and zeta keeps on varying, either it charges or discharges uncertainty. Following are the zeta values and their respective distribution operating cost. Next is the case study, which is a practical case study where we have randomly generated various scenarios of EVA and RES uncertainties. We have taken historic data of output power of RES where Solcast application is used and their graph represent the following result. Now let us move to the conclusion.
So, from the above information, we can conclude that the proposed model showcases the significance of electric vehicle aggregators in optimizing the operational cost of the distribution companies. Through stochastic optimization and integration of renewable energy sources, we can conclude that the model addresses uncertainties, demonstrating that higher scenarios counts yields more accurate optimized costs by charging the electric vehicles at lower prices and discharging them at higher ones. The model also emphasizes the economic efficiency. Furthermore, we can conclude that the practical applications incorporating historical data and uncertainty analysis highlights the robustness of the charging strategies. Overall, the model underscores the economic benefits and theoretical relevance of electric vehicle aggregator flexibility and zero uncertainty, positioning it as a futuristic optimization approach for dynamic environments. Thank you.